Okay, welcome for those who are here and for most of you who are watching this as a recorded webinar. This is the week 5 webinar. This is a week 5 webinar. And let me tell you what the plan is today. So the first thing I'll do is I'll answer any questions you have. Always happy to do that. And that could be about, stuff that you've been doing recently in terms of the, assignments or whatever, but even more importantly, what's the big thing that's due on Sunday? Hopefully y'all know.
Our project.
Yeah, the project. Okay. So this is a, good time. Definitely have a chance to, answer any question about the project, because that's the biggie that's coming up. It's a big part of the grade and it's important. It's what I've found when I talk to people like 5 years after, I find that when I ask them what was the most helpful thing in the class, that helped you learn the most, project is the biggie. So I've definitely learned that the project is the most important part of the class in terms of really learning long-term, because that's something you'll remember for maybe forever. So projects are important. So definitely, if you have questions about the project, I'll be happy to help you out. And I want to let you know again, it's due on Sunday, but I strongly recommend you send me a first draft. And that has to be sent to me by Thursday at 8 in the morning. But I read it on a first come, first read basis. So if you send it to me earlier than that, I'll read yours earlier probably, and then you'll get feedback earlier. So you won't have to wait till the last minute to get feedback. Because if everyone sends it Thursday morning, I may not get feedback for a couple of days for the last one who sent it, is the idea. So again, if you send it earlier, then you'll get earlier feedback. Okay, so that's, the earlier the better. And hopefully you're making a lot of progress on that project already, and you're writing out your draft. Okay, that's always how it's supposed to be. So so that's a big deal as a project. There's also the assignments, and those are important too. I want to let you know that a lot of people have have a little challenge on the discussion assignment this week. That's due on Sunday also. So that one you want to do a little early and ask questions if you need them. I'm here to help. Kyle has office tutoring hours and can help also. So we can definitely, make it work for you. So just a few things is that, I gave a sample, which I always do. I always put a sample whenever there's anything real to do. And don't just copy and paste my sample. And I want to really make it clear, if you copy and paste my sample, there is probably a 50-50 chance that it will not save, because in my sample I put some sophisticated I wanted to make it look pretty. You don't have to make it look pretty, but I'm the teacher, so I should make it look pretty. And some of the pretty stuff doesn't copy and paste. So don't just copy and paste what I wrote. At least retype if you want to put some of the language in, but don't do the copy and paste, because that almost never works with the formatting of especially the lowercase hat, which we'll talk about later. So then we'll get into sampling distributions, which is kind of a big theoretical, very important, but it's a theoretical thinking that's like we're going to be talking about the rest of this whole course. So then we'll get into what is a biased and what is an unbiased estimator. Then we'll get into the big theorem, and that is the central limit theorem. It is the most important theorem by far for statistics. And it actually has 3 pieces. So I'm going to go each of the 3 pieces and talk about them. Central limit theorem for means. So when you have quantitative data, the central limit theorem for proportions. That's when you have the yes/no survey question. And then also central limit theorem for sums. And that's when you're most interested in the sum or the total of the answers. Okay, and we'll talk about those. And means and proportions are the most important of the two. The sums is one minor thing we probably won't use again, but it's important just to know for this particular chapter. Okay, so that is the plan. Are there any questions about anything? And for those who just showed up, thanks. Any questions? And if there's not a question, we don't quite have enough to do what I was planning on doing, so I'm going to try something else. Okay, so what I want you to do now, and it shouldn't take you long, is I want you to go online. Hopefully you're all online, otherwise you can't be on Zoom either. But hopefully you can get a second screen or whatever. And I want you to find the ages of 3 actors. Could be anyone. Just want you to find the ages of 3 actors. It's very easy. You could just go to Google, say, what is the age of, and then whoever the actor you want to look at. And actor, actresses, I make it plural, but actors, actresses. Not even sure what you use if it's a they instead of a. I don't even know how to do the grammar on that one. If it's a non-gender one. So it shouldn't take more than a minute or two, to go online, find the age of your 3 actors, and then type in the 3 numbers. I just want 3 numbers. I don't need the people. I want 3 numbers typed into the chat box for each of you. And Kyle, I'll let you do it too. And I'll put in some that you got. All right, here we go. So we have 48, 68, and 50, if I remember right. Yep, 50. That was one person's findings. Another was 61, 27, 54. And a third was 36, 28, 31. Any questions so far? Okay, now what I want you to do, and you may need the calculator for this, is you will need the calculator, is I want you to find the mean and the standard deviation for the 3 actors you picked. And if you want, just the mean is enough. You don't have to find the standard deviation. That you might be able to do simply with the calculator. You might even be able to do it in your head, but probably not. But you should be able to find the mean. And then when you have the mean, put the mean in the chat box. Oh. Okay, so I'm gonna, yeah, I don't think 7.3 was right. Let's see. That's much better. None of you pick children. Okay. So we had a 31. I'm just going to do 1 decimal, because that's not, the point isn't lots of decimals. And then we had a 47.3. And then we had a 53.3. Hopefully I got that right in terms of who did what. 55. 55. Yeah, I'm trusting you. I'm not doing the arithmetic in my head. Okay, so notice that you all got different means. By the way, would you expect that you'd all get different means? Yeah, you should expect you get different means. I mean, you get different actors, right? Probably going to have different means. So I want to, I think I can do it. This one, there it is. There we go. One very important part of this chapter is the notation. And all of you found an X bar. Does that make sense? Okay. And by the way, if I asked 1,000 people, could they all have different X bars? Yeah. Yeah, because they might all have different age actors and they could have different X bars, right? All right, they're all over the place. Is that clear? Any questions on that? All right, so what we can now look at is, let me look at this. I'm going to look at the set 55.3, comma 47.3, comma 31.7. And let's make that bigger so you can see it. Okay, so this is a set of sample means. Is that clear? Okay. When you have a set of numbers, you could do statistics on that set of numbers. So we only had 3 of you do it, but we can look at, let's consider the set of all possible sample means of actors' ages but we're going to restrict the sample size of 3. Okay, there's probably millions of them. Okay, there's so many different combinations of actors that you can pick. Right, there's thousands and thousands of actors, and if you pick 3 randomly selected actors, there's so many ways of doing that. Any questions on this idea? Okay, so one thing is, you can think of the set of all actors. That's the population. Okay, and it has a distribution. And then there's a set of all sets of actors with sample size 3. Okay, and that's actually going to be a bigger set than the set of actors. And it will have a full distribution, including a mean. It'll have a standard deviation, right? We could find the mean of these 3 means, right? You could find the standard deviation of these 3 standard deviations. In theory, you could find the mean of all possible sample means of size 3. You could find the standard deviation of all possible sample sizes, samples of size 3. Have I lost any of you on this idea? Any questions on this? Okay, so the distribution of all sample means with the same sample size is called the sampling distribution of the sample means. And let's put that in red because that's the big thing here. So sampling distribution is the distribution of all sample means with the same sample size. So in our example, sample size 3. Any questions on this idea? Okay, so when you're looking at statistics like your project, you think about your project, you're all taking a sample, right? And you're going to be looking at your sample mean, and that sample mean is going to be one item of the sampling distribution. Any questions on that idea? Okay, so that's the sampling distribution. Okay, notice that this is all just kind of an idea. We don't, right now, we haven't calculated anything. I mean, I did some examples, but we did, 3 examples out of the possible, maybe millions of possibilities. So we're going to get into how do you understand the whole thing? How do you try to understand the distribution of all possible ones? The sampling distribution. Any questions on that idea? Okay, so I'm going to show you some notation now. So one is if we want the population mean of the sample means, then the notation we're going to use for that is this mu sub x bar. Okay, it's the population mean. That's how you read mu. X bar is a sample mean, so it's the population mean of all possible sample means. Any questions on that? Okay, it's pretty abstract so far, isn't it? I tried to do an example at least to see it, but lots of letters and stuff. Okay, then there's also the population standard deviation of all possible sample means. And that, since it's a standard deviation, we use sigma. So that was supposed to do it. Doesn't like it. There we go. So we're going to use sigma. Sigma is the population standard deviation. X bar is sample mean. So it's the population standard deviation of all the possible sample means. So you have this long list of sample means, and you can find the standard deviation. Any questions at all on this idea? Any questions? Okay, so kind of the goal is to understand this and to even use it a little bit, and we'll do that. Okay, so now, if we consider the collection of all possible sample means, this is its own data set with a very large size, usually too large to even imagine. So for example, if you looked at, I don't know, people in California and you did a survey of, let's say 50 people in California, and I don't know, maybe asked them how much money they make. Okay, maybe we'll call it adults in California. And we looked at the sampling distribution of that. Then if you look at all the possible sample means, we don't have a word for a number that big, how many there are. It turns out that's how big this sucker is. Okay, it's more digits than you've ever seen in your life. So we're not going to actually do it in terms of item by item, but we're going to be kind of looking at it, and there's going to be a nice theorem that tells you how to deal with it. Okay, we can consider the distribution. We talked about the mean, and we talked about the standard deviation of these sample means. You could also talk about the shape of the distribution. You could draw a histogram. and say, hey, is it skewed left? Is it skewed right? Is it a uniform distribution? Is it a normal distribution? What does it look like? Does that make sense? Any questions so far? Okay, so this is an important vocabulary word coming up. So the standard deviation of all possible sample means, we did sigma sub x bar, but we also have, because it's just too many words to say, we call it the standard error. So the standard error is the standard deviation of all possible sample means. Any questions so far? Okay, just want to let you know, if the standard error is small and you take a sample mean, then you're likely to be close to all the other sample means. That's what it means to have a small standard deviation, doesn't it? Any questions on that idea? Okay, so having a small standard error means that your sample mean is very likely to be the same as all the other sample means. So that's going to be an important idea. Okay. So just in general, we only talked about means, but you could talk about other things. You could do a sampling distribution instead of for a mean. You could do it for a standard deviation, or you could do it for a proportion, or you could do it for a minimum. So whatever you want to do, you take a sample and you look at that statistic. And if you look at the sample, you could look at the sampling distribution for sample sizes of size n for that statistic. Okay. And that's we call that the sampling distribution for a statistic. Any questions so far? Any questions? Okay, a lot of vocabulary to start. So please stop me if there's any of these words that don't make any sense. Okay, so the next one is an important one. Is we say a statistic is an unbiased estimator for a parameter. So for example, for a mean or for a minimum or for a range or for the first quartile, okay? If the mean of the sampling distribution for that statistic is equal to that parameter. Okay, so that's a lot of words there. Helps to have some examples. So an example is the sample mean turns out to be an unbiased estimator for the population mean. So if I took a sample of, let's say, 20 actors, and I looked at their average age, okay, and I did a random sample of 20 actors, and I looked at their average age, then that average age that I just looked at is actually not a bad guess for the population mean age. So the question is, am I going to upload the document for us to utilize? I don't usually upload the document. All this, first thing is this stuff is on YouTube, so you can re-see it. It's also, all this stuff is in the book. And so all these definitions in the book. I usually don't upload it because I make changes and stuff for various reasons. And the other reason is this contains a secret word. And I want people to watch the video. So, but if you have any questions, I'll pop it in for you. Okay, so please ask questions. Obviously, if you have a question, no one's going to be complaining. So please ask questions. Okay, and all this stuff is in the book, by the way. And again, you can always rewatch it. You can go to that part on YouTube. Yeah, so if you have a question, email me. I'll send you whatever you want. How's that? Sound good? Okay, so let's go through. So the sample mean is an unbiased estimator for the population mean, which means that if you have a sample mean, that is a really good guess. It's your best guess for the population mean. On the other hand, the sample range is a biased estimator for the population range. Okay, so for example, if I surveyed 10 people, just randomly, let's say in California, and I asked them how tall are they? And I looked at the range of height of those 10 people. Is that a good guess for the range of height of all people in California? So if you think about all people in California and you look at the range is the tallest minus the shortest, right? Does that make sense? The shortest person in California was just born, almost by definition, right? Not that many inches tall, a few inches tall. Okay, maybe, I don't know, 15 inches tall or something. Really short. Maybe, actually, it could be some kind of really mini infant. Might even be 6 inches tall. Okay, on the other hand, the tallest person in California, it's gonna be like 7'5" or something. And the range might be 7 feet. But if you randomly pick 10 people, you're almost never going to get 7 feet as the range. So that means using the range of a sample of size 10 is a terrible estimator for the range of the population. Does that make some sense? Okay, so the range is a biased estimator. I'm not proving this because it's a lot of math to prove anything of this stuff, but you can trust me on this. And hopefully it makes sense that the range would be a terrible estimator, a sample range for the population range. On the other hand, the mean is not a bad estimator. It's a good guess. Any questions before we move to the most important theorem of the entire class? Any questions? Okay, so here's the central limit theorem, and it's in pieces. And this is the central limit theorem for means. And it says the following. First is a sampling distribution for sample means from samples of size n has the mean of all possible sample means is equal to the mean of the population. That's actually another way of saying that the sample mean is an unbiased estimator for the population mean. Okay, so this is very important. Any questions on that? So that means that if you're going to conduct a survey like you are conducting for your project, or you conducted, then your sample mean is your best estimate for the population mean. Any questions on that? Okay. It's not biased as long as you took a random sample. All right. But one of the things you might want to say is, how good an estimate is it? Does that make sense? It's the best estimate, but how far off might you be? Okay, you might be too high, you might be too low. On an average, it's perfect, but you're not doing an average, you're going to do one sample. But if you did a trillion samples, they're going to average just right. To many decimal places, they'll give you the population mean. But you don't have time to do that. You're only going to do one sample. For your project, you're doing one sample. If I asked you to do 100 samples, you just quit, you drop my class probably. Because it'd be way too much work. Do you agree? Okay. So if you want to see how far off you might be, then how far off you might be is like, if you're far off from the mean, often, then what does that tell you about a different statistic? What's the different statistic that I'm kind of referring to? Not the mean, but who remembers? It's a biggie. Y'all better know for your project. Not the median. Median's a small one. Z-score is kind of nice, but much bigger. The biggest one for your project after the mean. Standard deviation. Yeah, the standard deviation. If you have a small standard deviation of the sampling distribution, then that means that your sample mean is likely to be pretty close to the population mean. Because that's what a standard deviation tells you, is how likely you are to be close. Do you see? Okay, so you'd like it to be small. You want to see the really important and good news? And that's B. And that is the standard deviation of the sampling distribution for means is equal to the standard deviation of the population divided by the square root of the sample size. And that's really important. So for example, if you did a study on heights, and let's say the height of people in California, let's say the standard deviation of the height of people is, I don't know, maybe 28 inches. I have no idea, but let's say it's 28 inches because there's little babies and there's tall people and stuff. Okay. So if that was, let's go 20 inches, I think is more likely. But if you asked 100 people and you took their average, then the sample mean is likely to be close to the population mean, because if you take 20, which is the standard deviation we just talked about, and divide by the square root of 100, square root of 100 is 10, 20 divided by 10 is 2. And now you're likely to only be 2 inches off from the population mean. So having a small sigma sub x bar is good because it means that you have a good predictor using your sample mean to predict the population mean. Any questions on that? Very important piece. Okay, so now here comes the next biggie. This is a really important one. And that is, in fact, let's make it bigger. If the population distribution is normal, or if the sample size is large, in our class, large, our definition means for, if you're doing a quantitative data study with means, then our definition of large is a sample size greater than 30. By the way, where have you heard greater than 30 in this class before? I've said it many times, and I told you we're going to get to it later, and now we're there. Yeah, project 1, I told you had to have more than 30, so 31 is the smallest number. And the reason I told you is if you have greater than 30, you actually have a large enough sample size to do good stuff. And the good stuff we can do is that the sampling distribution of the mean is approximately normal. Okay, and that's when you have a quantitative survey question. Quantitative data, not yes, no, for example. Okay, any questions on that? So the good thing about being approximately normal is that it's approximately normal, then we can use the normal distribution calculator to compute any probability we want. Whereas if it's just some sampling distribution and we didn't know anything about the distribution, you can't do any calculations. You're never going to get probabilities because you just don't know. Any questions on that idea? Okay, just as I want to give you a heads up though, this is very important. And that is, do not use the central limit theorem or even refer to it for your project 1. You're not ready. That's not what project 1 is supposed to be about. So I just want to let you know, don't use this stuff for project 1. Really, project 1 is on the first couple chapters of the book. Any questions at all? This is so important, the central limit theorem. It is the most important theorem of the entire class. Okay, do you want to see a very important application that I actually personally, truly personally, not for my job, personally used on Friday. And I personally used it to make money. Okay, not for work, by the way, but literally to make money. I like to make money. Do you guys like making money if you can? If you have any, most people do. So let me talk about making money. Okay, and I have some examples. All right, let's suppose you put $10,000 in the bank. Okay. What is the probability you're going to end up losing money after 1 year? Okay, and so let's assume it's a FDIC insured bank like Bank of America or US Bank or Wells Fargo or one of those banks. Okay. So what is the probability of losing money? Losing money means that your X, as in the amount of money you make, is less than 0. And that probability is 0. Okay. Because FDIC insured means even if the bank goes out of business, the government will give you money. Okay. So that probability is 0. Is that clear? But what do you think? What do you think the mean interest is on your money? If you put money in the bank, how much interest are you going to get? What percent? Okay, 0.5%. I haven't looked this one up recently, but maybe 1%. Not 0.01%. Could be 1%. I think it's more like 1%. It used to be 0.5%, but it's gone up a bit because of inflation. Let's call it 1%. Sound good? Is this a good investment? Okay, it depends. All right. So there's two things to look at. One is, let's suppose that if you lost money, then your entire future is gone. Let's suppose you're going to need that money to maybe pay for your education. And if you lose money, you're going to have to drop out of college. Okay, then you need that standard deviation to be 0. Does that make sense? So that would be one reason why maybe that would be a good investment, because your standard deviation is 0. On the other hand, if losing money is not that big a deal, I mean, it sucks. No one likes losing money, but if it's not going to destroy your entire education or something like that, it's just going to make you be in a bad mood for a week or two, then that's a whole different thing. Okay. Then you say, well, I'm going to get a 1% interest. And by the way, what's inflation rate right now? Do you know? Just a guess is fine. What's the inflation rate? You can pop in the chat box if you want. Yeah. Okay. I see 5%, 8%. Okay. Let's say it's 6%, for example. Okay. And you're getting interest of 1%. Okay. Your actually value is going down. That makes it a pretty bad investment, right? But at least you know what's going to happen, right? Okay. So here's another probability. Okay. I'm giving you some financial advice, by the way. I try to make things real. This is real. And by the way, I use this stuff. Like I said, I actually didn't put 10,000 into my investment. I put 7,000 into my investment. 5,000 in my investment. Sorry, on Friday. I did just invest $5,000 on Friday. Okay, so suppose that you put your $10,000 into a randomly selected stock. Okay. Now, over the past 20 years or so, the mean for stock is 9% increase up. The standard deviation is 20%. Okay. Let's assume the stock returns are normally distributed. What's the probability you're going to end up losing money now? Okay, how do we figure that out? And you won't do it in your head, so what do we have to do? We do this a lot in this class. Yeah, we go to the calculator. Okay, and we're assuming it's normally distributed. So we can go to the normal probability calculator. The mean is 9. I'm using the units of percents. Makes it easier to type. Standard deviation was 20. Any questions so far? We lose money if it's less than 0. So the low is negative 99999, a bunch of nines percent. The high is going to be 0. Any questions on that so far? So as review, this is from last week. And I hit calculate. All right. So you'll notice I'm going to round to the nearest whole percent. So it's about 33% chance. Any questions on that so far? All right. So that is going to be 0.33. All right. So if this was money where if you lost money, you're going to end up having to drop out of college. Is this a good investment? I'm hoping you all say the same thing. What do you think? Yes or no? Good investment or not? Okay, I was hoping you'd say no. If there's a 33% chance you're going to have to drop out of college because you had bad luck in the stock market, that's horrible. I hope you're not okay with that. That's like 1 in 3 chance of having to drop out because of an investment problem. Does that make sense? It's a terrible investment. Okay, yeah, you get a mean of 9%, but you got a 33% chance of losing money. All right, any questions on that? Okay, are there any other ideas on how you might invest money so you can get a higher mean and a lower standard deviation? And the hint is, what did we just talk about? What I tell you was the biggest theorem. What might we do? Any thoughts? See jumping in. Okay, so let me tell you. Okay, so if you want a higher mean and a lower standard deviation, especially in the long term, by the way, then what you can do is you can, instead of invest in one stock, you can do what's called a diversified investment. So it's kind of like randomly picking a bunch of stocks. Okay, and the way to do that in the stock market, anyone know what that's called? How to do that? You don't know, I'll tell you. It's called a mutual fund or an index fund. Okay, it's not quite random, but that's the idea, is that you take your money, you put it in a mutual fund or an index fund, and that invests it in many, many stocks so that your probability of your standard deviation is going to go down because we can use a central limit theorem. And you could divide by the square root of the number of stocks that get invested. So here's what you can do. And I'm going to do one that you might have heard of. Okay, so suppose instead you put $10,000 into a Dow Jones index fund. If you don't know what Dow Jones means, it's the Dow Jones is 30 stocks. And I know it's not quite over 30, but we're gonna let it go. Okay. Now, what's the probability of losing money if you put it in the index fund? Okay. And we are going to assume that the Dow Jones is a representative sample and that the stocks are independent of each other. And when you say independent of each other, you often call that a diversified investment. And again, I've done a lot of investment in my life. and diversified investment's important. Otherwise, you could just lose it all. Okay, so our mu is 9, our standard deviation is 20. That's the same, our sigma is 20. But now what we can do is say we're not looking at a single stock, we're looking at 30 different stocks. So we're talking about the mean of the stocks is how our investment's going to change. Any questions on that idea? And we can assume, we can say that's approximately normal. It's not quite over 30, but we'll call it close enough. The central limit theorem says that the mean of all possible sample means, the mu sub x bar, is equal to mu. So that's still a 9. So we're still getting a mu of 9, which is really good, much better than 1%, right? Our standard deviation now is going to be the standard deviation of the population, which was 20, divided by the square root of the sample size. The square root of the sample size is the square root of 30 because we're investing in 30 different stocks. It's kind of like taking a sample of 30 people, but now it's 30 stocks. Now I did this in my own calculator. 20 over root 30 is 3.65 approximately. Any questions on that calculation? All right, so here's a big deal. This is much smaller than 20, 3.65. Our standard deviation is a lot lower, and that's important. So now we can put that into our calculator, but what's changed now is the standard deviation is now 3.65. Our low is still negative 99999. Our high is still 0. We're trying to find the probability of losing money. Our probability is what we don't know. So any questions before I hit calculate? Okay, I hit calculate. And then all of a sudden, everything has changed. Instead of a 33% chance, we have less than 1% chance. Any questions on that? Okay, now we are assuming that things are independent of each other, which isn't quite right on the stock market, but it's way too complicated for me to do in just like a lecture. You need to really take a full business and economics class to understand a little more or a lot more, but we'll make that assumption. Okay, and we get less than 1%. Okay, 0.0068 about. So this is a much better investment because we still have a 9% as our mean. But now our probability of losing money is almost nothing. Any questions on that? Okay, now you have to truly understand diversified investments. But if you do, then it's silly to put your money, especially any significant amounts of money, in the bank. Put a little bit for the, month by month, stuff that you're buying in the market or whatever. But is it normal distribution in the real life? So the answer is yes, in the long term, not necessarily 1 year, but if you did say a 10-year, like for retirement, then normal is very, very close. Yeah. So again, there's more complications. So I will let you know, I'll even tell you. I told you I invested on Friday. I invested in a mutual fund, but I invested in an India mutual fund. And that's for different reasons. Okay. It takes away some of the independence, but that's more math when it comes to population and looking at the demographics of India right now. Has a lot of people in the next 10 years that are going to be working. So I think that they're going to do well. I might be wrong. Who knows? There could be some ugly war or something, but that's what I just did on Friday is I invested. You could talk to me in 10 or 15 years and hopefully, this is all right. And, but I did a mutual fund because I'm not going to invest in a single stock. That's way too dangerous. Okay. And by the way, I don't have all my money in India. I wanted to be diversified. So I wanted some international funds, some America funds, some real estate funds, all kinds of different funds, because that allows you to be diversified. So your probability of losing money is much lower. Any questions on that idea? Okay, it's pretty deep. Okay, on the other hand, by the way, if you invest in a mutual fund, probability of losing money is a lot less. The probability of winning a whole lot of money is also a lot less. So there's a good chance you're going to get close to 9%. There's a bad chance you're going to get, 25%, because you're not going to be far from that 9%. Any questions on that? Okay. And by the way, I use statistics a lot for investments, and it's helped me a lot. Okay. And I keep it somewhat safe, so I'm not a billionaire or anything, but I have made a lot of money in the stock market and other places. Okay, and nothing like immoral or anything, but it helps. All right, so here's the next question. Let's suppose that you want your standard error to be equal to 2. How big a sample size do you need? Any questions on the question? All right, so what we're going to do is we're going to put it into the formula. So our standard deviation was 20. The sample size is what we don't know. Let's call that n for number, sample size. That's what everyone uses for sample size, by the way. So it's 20 over root n. Sigma over root n was the formula. And we want that to be, not 0.2. No, 2, sorry. I just had that wrong. There we go. So we want that. So now we have to do a little bit of math. We're going to multiply left and right by root n. And we get 2 times root n equals 20. I'm going to divide by 2, and I get root n equals 10. And then I'm going to take a square of both sides to get rid of the root, and I get n equals 100. I say, what number? If I want a number, square root is 10. That number is 100. So that says that I'm going to need to have a sample size of 100 if I want the standard error to be 2. Any questions on that? Any questions? Okay, easy enough? Okay, so again, I'm showing you some applications. I'm not showing you the biggest application, because the biggest applications come in next week and the week after. But I can give you a kind of a hint on what's going to happen. In the real world, in statistics, you do a study and you collect data, just like your project. And what you want to do is you want to say, well, you've just done your project, you got your sample mean, and then you want to say, well, how far off is the sample mean from the population mean? And next week, we'll be able to answer that question. Okay, and it's not going to be a definitive answer. We're going to be able to say, well, there's this % chance of it being only this away from the sample mean, from the population mean. So that's kind of the main point of this. And the other thing that we'll look at, which will be the next week, is let's suppose, I like to use a kind of the COVID example. Let's suppose you have a new medicine. Okay, so you work for a pharmaceutical company, and you think your medicine is going to reduce the amount of time that people have COVID. So once you get COVID, you're going to take this medicine, and instead of having it last for many days, maybe it'll reduce it to maybe 2 days instead. Does that make sense? So then what you're going to do is you're going to need to, if you have a pharmaceutical company, you're going to need to show that your medicine works. Now, what you can't do is give it to everyone in America, because that's against the law. You might kill everyone, for example. What if it killed people? So instead, what you do is you do a sample. And you might sample maybe 1,000 people, volunteers who will take it, who have COVID, okay? Or maybe 100, who knows? Then what you're going to have to do is you're going to have to say, based on this, my 100 people I gave it to, they healed a lot faster from COVID. They got better than the average. Okay, does that mean that the whole population will get better faster? And the idea is you want to show with high probability that it does. Okay, you're going to say that it'd be too unlikely to get what you got. So therefore, we're going to say that, yeah, we got good evidence to say that with our medicine, that anyone who gets COVID and takes the medicine has a much higher probability of getting better faster. Any questions on that idea? Okay, and that's the main application that we're going to be doing in this class, by the way. Okay, not just COVID, but everything about that type of thing. All right, so now comes the next central limit theorem. We've talked about means. Now it's time to talk about proportions. Okay, so when we talked about means, remember, a mean comes from a survey question where the answer to the survey question is a number. So that might be, how old are you? How tall are you? How many, how much money do you have in your wallet right now? That kind of thing. Okay. Those are all numbers that someone's going to answer. A proportion is when the answer is yes or no. And we use P for population proportion. We've done that, but we've already seen that. And now I want to let you know, for sample proportion, we're going to use a P with this little thing that looks like a hat. And the way to say this is P hat. And that'll be the sample proportion. Any questions on that so far? Okay, I want to give you a heads up. Typing P with a hat on top is really hard. Okay, if you're not like a computer expert, then it's really hard to learn this. Okay, it takes some work. So for you, it is fine. I'll never take off points if on an assignment, like on the discussion post or whatever, if you write P HAT instead. Because then it'll be clear what you mean, and that's the same thing as P with a hat on top. Sound good? Okay, but don't write P, because that's the population proportion. So you have to say that it's P hat, either by spelling it out with P HAT, or if you can figure out how to do it in the computer, that's fine too. But it's not easy to do it in the computer, especially on Canvas, by the way. Good luck. It takes a lot of work. Okay, and that's the sample proportion. All right, Q is the letter we're going to use for 1 minus P. So for example, if you have a 40% chance of winning the game, what's your percent chance of losing the game? Hopefully you can tell me. It's a win or lose game, by the way. You have a 40% chance of winning. What's your percent chance of losing? Not 50, 60%. Good. And that's because 1 minus 0.4 is 0.6. Do you see how that works? So you look at Q, often we'll call that the probability of success, even though it may not be a good thing, but it's the probability of saying yes to the survey question. And Q is the probability of saying no to the survey question. Any questions on that? And that's always 1 minus p. Okay, now comes the big theorem. And this is similar to the central limit theorem for means, but we have proportions instead, so the formulas are going to be different. The sampling distribution for the sample proportions for samples of size n has mu sub p hat. That's the population mean of all possible sample proportions. Remember, every sample proportion is a number like 0.6 or 0.3 or 0.17. So you could take the mean of those numbers. And that says that the mean of all possible sample proportions of the same sample size is the population proportion, which is another way of saying that the sample proportion is an unbiased estimator for the population proportion. Any questions on that so far? Any questions? Okay, so here comes the big harder one, and that is sigma sub p hat, the population standard deviation of the sample proportions of all possible is equal to the square root of pq over n. And remember, q is the population proportion of no answers. Notice, by the way, and this is very important, that we have a square root of n in the denominator. And that's the same thing that we had for the central limit theorem for means. So it's going to have that same idea that if you want to have a better estimate for the population proportion, then a larger sample size will make that happen because our standard deviation will go down. And that means that you're more likely to be close to the population mean of all sample proportions, which happens to be the population proportion. Anyone lost on what I just said? Okay, now comes the next piece of the central limit theorem. This is where a lot of people make a mistake. That is, if NP and NQ, and by the way, NP are the predicted number of yes answers, not the proportion, but the number of yes answers you expect to get. And NQ are the predicted number of no answers. And if they're both larger than 5, not 30, 5, then the sampling distribution is approximately normal. Okay, so if you want to know how many you need to survey to be able to use the central limit theorem and use the normal distribution, then you check NP and NQ and make sure they're both bigger than 5. Okay, here's something I want you to do. I want you to put a promise in the chat box. And by the way, if you're watching this as a recorded webinar, I want you to write this down on paper. And you all have to do this. Write this in for a yes, no answer to the survey question. I will not use the number 30 to see if the sample size is large enough. You must write that down right now. I want you to type that in or write it down on paper if you're watching this recorded. I'll make this bigger for you. I put it in red. It's one of the biggest mistakes that I will see in using the central limit theorem is they want to find out, is the sample size large enough? And they say, oh yeah, it's bigger than 30. But if it was a yes, no survey question, it's wrong. And you will lose points if you do that. Got it? And I can't tell you how many points I have had to take away, and I hate doing that. So I do everything I can to try and keep you from making that mistake. Okay, let me give you kind of an example of where this becomes really important. Let's suppose you were interested in the percentage of Americans who have been to Iran. Okay, by the way, has anyone been to Iran? Yeah, some people have, not you guys. I haven't. I have no interest, by the way. Too scary being an American there. Okay, but some people have. Actually, I know someone I work with that's been to Iran. Okay, then if you wanted to find out how big a sample size you need so that you can use the normal distribution, you're going to need a very large sample size, because the proportion of people who have been to Iran, you would guess, be very small, not even 1%, right? So even if it was 1%, then you'd have to make sure that NP was greater than 5. And by the way, being bigger than 5 means so that would mean 1% of a number is bigger than 5. That number better be bigger than 500. And you would need a very large sample size in order to be able to have a normal distribution that you can use. Any questions on that? Okay. All right, so here is an example that I'm quoting Gallup poll, which I'm allowed to quote them. And the question is, do a majority of women younger than 50 who have used dating sites or apps have received unwanted sexually explicit messages or images on these platforms? Okay. So let's find out. Let's talk about it. Okay, you're saying yes, but my guess is your yes was a guess, right? That you don't right now, without reading more, have statistical analysis for that, right? Okay, maybe do, but I doubt it. But let's do it. That's the whole point. So here's the question. If 50% of all women younger than 50 who have used dating sites or apps have received unwanted sexually explicit messages or images on these platforms, then what is the probability of a randomly selected 872 women younger than 50 who have used dating sites or apps? What is the probability at least 56% of them have received unwanted sexually explicit messages or images on these platforms? Okay, and by the way, in the Gallup site, of their 872 women younger than 50 who've used dating sites, 56% of them said yes. Any questions on that? So that's why I'm asking this question, is if it really was not the majority, which means exact 50% would be the highest number not being the majority, right? You have to be more than 50% to be not the majority. Okay. Okay. By the way, does that mean you have to be at least 51%? Yes or no? If you want to be more than 50%? Yeah, the answer is no. So let me give you a personal example. You need, hopefully you need the majority of voters to win an election, right? Now, and if you look at the people, when I ran in my first election, when I ran for office, if you look at the people who voted for me or the other person, Wendy, actually, sorry, it was Barbara, not Wendy. It was Barbara. Then I won, but I didn't get at least 50%, 51%. How'd that happen? Any guess? Okay, if you don't know, let me tell you. I got 50.3% of the voters voting for me. And I won because I got over 50%. It wasn't 51%, but it was over 50%, even though it was just a little tiny over 50%. That's all you need. Any questions on that? And the same thing when you're talking majority, 50.00001 is still a majority. Any questions on that idea? Okay. So let's find this probability. So first thing is let's find NP and NQ to see if we can use the normal distribution. NP, N was 872, right? Survey of 872 women. P is our 0.5 because we're assuming, we're saying, let's say if it's exactly 50%, that's P. And 872 times 0.5 is 436. And NQ is 872. 1 minus 0.5 just coincidentally happens to be 0.5. And I get 436. They're both much larger than 5. Do you agree? So that means, yes, the sampling distribution is approximately normal. Any questions on that? Okay, so now what I need to do is I need to use these formulas. Mu sub p hat equals P. I can say that P hat has an approximately normal distribution of mean 0.05, that's our P. And then sigma sub P hat is a square root of PQ over N. So I take the square root, P is 0.5, Q is 1 minus 0.5, which happens to be 0.5. N was 872. Any questions on that? All right, now I want to say, what would the probability be that at least 56% have said yes to the survey question? Have you received unwanted sexually explicit messages or images on these platforms? So now what we can say, since at least 56%, then I can go to our normal distribution and say my low is 56% or 0.56. You could say the high is 1. You could also go 99999. It doesn't make a difference in this case. They'll both give you the same answer, it turns out, because 1 is big enough in this case. And then our mean is going to be 0.5, and our standard deviations is mess. So to do this, I need to go to my normal distribution calculator. My low was 0.56. My high was 1. The mean was 0.5. For the standard deviation, I need to calculate this thing. This is messy. So it's a square root. And then I'm going to go for, let's see what it was. 0.5 times 0.5 over 872. Any questions on that? Okay, that's the standard deviation. The good thing about this, and this is why I put the calculator in like this, I can just copy, I can paste it right into the standard deviation. I didn't have to worry about how many decimals. I just put them all in because that was easy enough. And I hit calculate. What do we see for P? What do you notice? It's really small, right? It's like 0.02% chance. Okay, so that's 0.02% chance. When something really has a small percent chance and it happens, you say, well, maybe something went wrong. Maybe our assumption was off. What do you think our assumption was? What was the one thing we assumed here? What was one of the major things we assumed, the major thing? Anyone see? Right here. We assumed that 50% of all women younger than 50 who have used dating sites or apps have received unwanted sexually explicit messages or images on these platforms. That was an assumption, okay? And if we have such a low probability of what we got happening, then we say maybe that assumption is just wrong. And maybe it's not true that 50% have received unwanted messages. Probably more than 50% have. Otherwise, we wouldn't have gotten this 56%. Any questions on that idea? I just want to let you know this is like, I know this is complex, complicated, but it is the most important idea of this whole course. Not about the unwanted messages, but when you get such a small probability, you say what might have gone wrong, and there's what went wrong. And you say, you know what? I don't buy this 50% thing. It's more than 50%. And then if you're writing an article, you're going to say the majority, because that's more than 50%. So the majority of women on dating sites have received unwanted sexually explicit messages or images. You see how that works? That's a big deal. Okay, and we're going to be using it over and over and over again in this class. Not next week so much, but after that, that's all we're doing pretty much. We're spending the entire rest of the class on seeing if an assumption has issues. And if the assumption has issues, then we're going to say our idea that it was greater than 50%. That's probably right. Any questions on that? Okay, and your discussion post assignment this week is going to ask you to do something like this. Okay, not this exact example, but this idea. Any questions? Because I want to make sure that you're all set up for this, because it's a lot of work and people have a lot of trouble, but here it is. Okay, then finally, our last thing to do is a central limit theorem for sums, which happens sometimes, not as often, but it does happen. So for sums, let me give you the example where sums are more important than means. Let's suppose you own a business. Maybe, since we're in Tahoe, maybe you have a gift shop, okay, for cool Tahoe stuff. Okay, and by the way, we have multiple shops like that in Tahoe. Then what do you care about at the end of the day? You own this business. What do you care most about? You own a business where you're selling, touristy gifts. What do you care about? Yeah, profit. Total profit. Okay, you don't care about the average amount of profit you get from each person who comes in. You care about the sum, the total amount of money that comes into that cash register, right? Minus the total amount that comes out. You see how that works? So that is like the classic example where the sum is much more important than the average. Okay, and there's others too, by the way, but that's like the one that most people understand. And here's what the central limit theorem for sums says. So the sampling distribution for sample sums of sample size n. So first thing is mu is the population mean. Who knows what this symbol is right here? Just to the left of the X. You know what that is? How to read that even? It's a symbol we use in math a lot. And you may have used it, you may not, I don't know, in your math classes that you had in high school or something. Let's see, I'll jump in. Okay, if you don't jump in, I'll tell you. Okay, first, this turns out this is a little confusing. This is sigma, but it's capital sigma, whereas this sigma is lowercase sigma, by the way. This is capital sigma, and the way you interpret it is it means sum. It means the total sum of. So it means add up all the x's. So the mean of all the sums is equal to n times the population mean. Any questions on that? And the standard deviation of all the sample sums is equal to the standard deviation of the population times the square root of the sample size. Any questions on that? Okay, so you should always be paying attention to the wording of the question. If it asks for a sum or it asks for a total, then that's the central limit theorem for sums. So look at the wording. What is it referring to? Okay, and then number two is actually the same as number two for the central limit theorem for means. And that is if the population distribution is normal, or if the sample size is large, greater than 30. So we're back to 30 again. Then the sampling distribution for sums is also normal. Any questions on that? Okay, sometimes we'll write sigma, tilde, n mu, that's this n mu, the mean, comma, sigma root n, that's the standard deviation. Any questions on the big theorem for sums? Okay. By the way, this is also one of the reasons why we deal with means instead of medians. You can't do this stuff with medians. It's like a whole different topic in statistics, and we just don't even go there. So once you're done with your project, you know, actually it could happen in the exams too, because those have earlier stuff. But none of our chapters from now on are going to talk about the median. It's all about the mean, and it could be the mean of the sampling distribution. It could be the mean of the population, but medians aren't going to happen in any chapters coming up. All right, so let me give you an example. Let's suppose that the average customer at a restaurant spends $33.23. Okay, let's say you might be the manager of your restaurant. Okay, and let's suppose the standard deviation is $9.22. Any questions so far? If 65 customers at the restaurant eat at the restaurant today, what is the probability that the revenue for the restaurant will be less than $2,000 and the total revenue? And then the second question is, what is the first quartile for the total revenue for a day? Any questions on the question? All right, so what we're going to do is realize we're talking about a total. So that's a very important word. Maybe I'll put it in red to remind you how important that is. When you see the word total, that means we're in the central limit theorem for sums. Any questions on that? Okay, so then that means I can use this formula right here, and I could say sigma tilde n. By the way, I can use n right here. We have 65 customers. What's important about the number 65? So that I can use n. What's important about that number 65? Yeah, it's greater than 30. And if the sample size is greater than 30, I could use the normal distribution. So then I take n, which was 65, and I multiply it by mu, which was $33.23. Then I take my standard deviation, which was 9.22, because that's from this formula, and I multiply by root n, or root 65. Any questions on that? Anyone lost? Okay, so next, I want to find out what's the total revenue be less than 2,000. So the lowest amount less than 2,000, you could just say a bunch of nines, negative. The highest is 2,000. Okay. By the way, the exact number of 2,000, don't worry about whether, at least if it said less than or at most, even though technically it has to be less than 2,000 with the normal distribution, since it is a distribution that is quantitative, okay, and a continuous distribution. That means we can just use 2,000. We don't have to pick a number less than that. We can use 2,000 as a barrier. And then let's compute. So I have the answers, but maybe I shouldn't write these in. I should pretend I didn't see them. So we have to go ahead and we have to go to our calculator later. The low now was a bunch of nines with a negative. The high was 2,000. The mean was 65 times 33.23. So 65 times 33.23. And I get $2,159.95. Any questions so far? The standard deviation was a bit messy. That was the square root of 9.22. Sorry, so the 9.22 times the square root of 65. Let's do 9.22 times the square root of 65. And that's a 74.33, etc. So copy and paste. Key is what I want, so I'm going to calculate. Okay, so what I get is 0.0157. Any questions on that? Okay, I want the first quartile. So for the first quartile, I don't know the high. I do know the probability, which is 0.25 for the first quartile. Any questions on that? And there we go. The first quartile is $2,109.81. Okay, and you should always use rules rounding. Notice that's a 2, so I don't have to change that 1. So I can put that right here. Any questions at all on this example? Okay, so that was the main stuff I wanted to talk about. The idea was there's a sampling distribution, kind of the idea of that. But the main three things: the central limit theorem for means, the central limit theorem for proportions, and the central limit theorem for sums. And those are the three central limit theorems, I guess you could say. So because I've said the main word, it's time for the secret word. And by the way, this is an L, not a 1. What does CLT stand for? Control is a good idea, but no, think about what we did today. What's today all about? Central limit theorem. Got it? So that's why it's CLT. Lowercase CLT will be the secret word. I try to make it relevant, but something you probably wouldn't just guess. Maybe you would, but probably not. So that's pretty much everything that we have. This is chapter 7. The good news is that this is an odd numbered week. So what does that mean you don't have this week? Yeah, no exam. Okay. But on the other hand, this is one of the hardest weeks of the whole quarter. Because what do you have? Hopefully y'all know. Yeah, project 1. So expect to spend a lot of time this week on project 1. Okay, I am going to stop the recording and then I'll open it up to questions.